Spark is, and that's the reason why Spark has been developed. But of course, Spark in many cases has extended and further developed concepts which were originally introduced with Hadoop. So that's why there's a lot of compatibility between the interfaces of Spark and Hadoop. And that's why it's quite handy to know Hadoop before actually diving into Spark. So that's why I talked about Hadoop before. And now we're going to dive into Apache Spark. Yeah, as always, a little review. So this is Hadoop MapReduce. So the basic concept of MapReduce is, like in this example, we have a reduce step and a mapping step. And the reduce function must satisfy these two conditions, associativity and the neutral element. The neutral element must exist so that the nodes which don't get any data do not affect the result. Otherwise, our result would be altered by nodes which don't do anything, which is not what you want. And so basically what we want is a monolith in order to work with Hadoop. Then we talked a little about the Hadoop distributed file system. As I said, it's the very same, which is used in conjunction with Apache Spark. It's a distributed, scalable, and portable file system. Distributed means everything, all data are distributed among several nodes. So usually all data consists of at least 3 nodes. And it's scalable, so because it's distributed, so it can scale up to very large amounts of data and still efficiently access the data. And it's also portable. It's quite easy to actually move it from one cluster to the other. Fully implemented in Java has these 5 services, consisting of master and slave services, where the name node is only there once, processing all the metadata for the stored data. Then you have the secondary name node, which is just assisting the name node, and the job tracker, which actually accepts the jobs from the MapReduce framework. Then we talk a lot about the architecture of Yarn. As I said, you can use Yarn also with Spark, and in a lot of situations it's a good idea to do that. The concept of Yarn is that you have a resource manager controlling the entire cluster. The client usually only talks to the resource manager. For every application, you have a separate application master. And the application master runs on any of the slave nodes and is deployed there by the resource manager. For every node, we have a separate node manager controlling all the resources of the node. The application master can request containers from the resource manager, but the resource manager is barely only forwarding this request to the node manager. So after the application master has gained the appropriate node manager from the resource manager, it will ask the node manager to open a container. And then if the resources are sufficient, this will work and it will get this container. And therefore there is this container launch context, and the application master will send this container launch context to the node manager, so the node manager can actually run the container. But this will only happen if the resource manager thinks that these resources on this node should be acquired by this application master. And then there is a regular report of the status by the application master to the resource manager. And the placement of the containers depends on the resource availability of the nodes as well as the data locality. So the container are preferred to be placed where the data reside, where the containers need to work with. And the number of the containers per node depend on the available resources, of course. Then we had this example for Apache Hive, which is basically some kind of SQL abstraction on top of MapReduce. And that's it. Okay, now let's talk about Apache Spark. first about the Spark ecosystem. Spark is used in conjunction with a lot of different frameworks. I will shortly introduce some of them here. So, for example, there is scikit-learn. This is a machine learning framework implemented in Python. And it's also used with Pandas. That stands for Python Data Analysis Library. As the name says, it's a library for data analysis. It's really used with Python. TensorFlow, maybe a lot of people have already heard about TensorFlow. That's a framework for neural networks or neural learning with the basic so-called tensors. That's why it's called TensorFlow. This can also be used with Spark. Then there's PyTorch, which is a Python library for machine learning. It's based on Torch, but Torch itself is implemented in Lua. So Lua is a scripting language. Maybe some of you have already heard about. And PyTorch is basically a Python wrapper for Torch. Then there is MLflow, which is an open source platform for the entire machine learning lifecycle. You know that in machine learning we have different parts of the lifecycle, like the training phase, so on, and this can all be managed with MLflow. There's also R. R is basically a programming language for statistical computing. As someone of you already worked with R, okay, some have, so some more, but not all maybe. Okay, so R is actually quite common in the industry, so it's not a waste of time to actually play around with R. Especially, of course, with a heavy focus on statistical computations. Then there's NumPy, which is a library for scientific computing in Python. Especially, of course, for numerical calculations and approximations. So rather scientific in this case. Okay, some impressions from this. So this is scikit-learn. And what you can see here is basically a principal component analysis of different species of plants. And you can see you can easily create this kind of plots out of the according data, like this here. I won't go into detail here, but as you can see, it's quite a powerful tool to actually create graphs, which this is really like paper ready, so you could just put it in your scientific paper and tell something about it. So it's quite useful tool for this kind of application. Then, just a very basic example for R, just to give you a little impression if you don't know R. So, like this here, it's just creating the bar plot, and you can see that it's easy, right? It's really easy. So, it's a script language, very easily applicable, and just takes you one liner to create a bar plot like this. Of course, you can do much more complicated things as well. But this is also often used in data analysis platforms, also for data visualization, where it has some powerful functions for. Then there are some analytics applications Spark is used with. For example, Apache Superset. Superset is a platform for data exploration as well as visualization. Then there's Microsoft Power BI for visualization and business analysis. Google Looker is a platform for business intelligence. Maybe you remember in the first lecture we had this differentiate a bit, so what's business intelligence, what's data exploration, what is data analysis, and so on. So Looker is more for business intelligence. Then there's Redash, which is a tool for connecting data sources. Tableau, it's a quite common tool in the industry also for data exploration and analysis, also for applying machine learning on data. And there's the DBT or data build tool. It's a special tool for data transformation, the so-called, they call themselves the T in ELT. Everyone knows what ELT stands for? Someone doesn't know what ELT stands for? Right, correct. Extract, load, transform. So That's some kind of basic approach to analyze extract the data, load the data, then to it. So DBT is the T in DLT. Of course, you can use different tools for the T as well. It's just the advertising slogan. This looks like this. So for example, this is Apache Superset. So you can see you can use it for data exploration like this. So here they have created a dashboard, and you can get nice charts out of the dashboard. You can also get visualizations of data, also geographic visualizations like this. So you can get a world map with different colors. And of course, graphs like this. Basically a data exploration platform. Of course, you can create customizable dashboards like this, and it takes some manual effort to actually get something like this. This is an example from Microsoft Power BI. You might say, well, it looks a lot like this one. Well, it does, yes, because I mean it's somewhat intersecting applications, right? So here it's also kind of dashboard. Controllers really love dashboards. So if you ever happen to work in a big company, then you know that they will always ask you for some nice dashboards with lots of parameters being somewhat shown on the dashboard. Here you can close the door because voice is coming through. As I said, it's quite similar. You can create all kinds of, summarize, aggregate, visualize all kinds of data which are somewhat relevant to your business, like the revenue, one by one, whatever, say for you. Controllers are always interested in so-called KPIs. I hope everyone has heard of KPIs, so-called key performance indicators. So the idea is that a KPI is somewhat correlated with what you want, right? So the idea is you have some kind of number, and you have this number together or gross, depending on its definition. So that even the manager which doesn't have in-depth knowledge of what his department or her department is doing can gain some insight how the performance is working out. But of course, KPIs can be a little bit misleading because, this assumption that this, this value reflects what you want is not always true, and it's really hard work to make it true. So, it's in reality, it's very, very dangerous to only rely on what the dashboard says and what the KPI says. But it's the way big companies are steered, because just the upper level management just isn't able to understand all the basics of all departments. So they just rely on this kind of abstraction. Sometimes it works good, and sometimes it doesn't work so well. But they are of course using dashboards like this for judgment. So be careful with what you put into your dashboard, because people will take it for granted. So if there's a curve going down, they will say it's bad, and if it's going up, say it's great. And, make sure that it's what you want to show, and it's the reality. Google Looker, also a platform for business intelligence. For example, here the search engine optimization. Here you can investigate access patterns for your website, for example. I mean, Google is of course, it's not only consists of the search engine, but of course, by far the biggest revenue Google gets from the search engine, which is still true for today. So that's of course why they have a heavy focus on search engine optimization, and also a lot of prepared layers for that. So you can use this to investigate and to optimize the websites. You can see, for example, where did the people come from which countries did they come, when did they leave the website, so how long did they stay on one site, and so on. And you of course can try this, for example, also to optimize the usability of your website. Any kind of optimized business, if it depends on the website. Redash is focusing on connecting data sources like this. So the idea is that you have different data sources and they are somehow need to be connected. And this is where Redash is able to create nice visualizations as well of how the different data sources are related. As I said, they always look a little bit similar because they have very similar use cases actually. Tableau, as I said, it's a very well-known tool for data exploration and analysis. I guess it's also quite expensive, so it's not for free, it's not open source, it's a commercial platform. And it also has some really powerful tools to work with data exploration. So it's on one side it's for understanding data, but then also it's for applying, for example, machine learning models on data and playing around with it. But it has a focus on visual understanding. So, for example, you can actually train a machine learning model without even knowing what a machine learning model is, which is sometimes a good idea and sometimes not. At least this tool is somehow offering you this. So you can do a lot of stuff without coding anything. Because many people who are not computer science persons do not like or do not want to code. So this is what Tableau is for, mainly. Then, as I said, this DBT, so the T in DLT, it has its own, we call it IDE, so development environment like this, and here you can find your transformations, which looks a lot like IntelliJ, and I guess it's intended. So, I guess there's also a plugin for IntelliJ. So you see there's a whole world around Spark and around this cluster computing frameworks. And there's even more. So I just want to let you know all of this so you have heard about it. Because it's certainly one or the other will stumble upon the way. For example, Elasticsearch. So this is not about storage and infrastructure solutions. Elasticsearch is actually an index for big data. So Elasticsearch itself isn't an analysis platform, but Kibana is, and Kibana is basically used in conjunction with Elasticsearch. So the combination of Kibana and Elasticsearch is often used for browser-based analysis of big data. Then MongoDB, or you know MongoDB, which is a document-oriented NoSQL database. Apache Kafka, we will also talk about this in detail later. It's also a very important part of the big data landscape. It's a distributed event streaming platform for data pipelines. By the way, it's named after Franz Kafka, who was a very famous German author. He did some very convoluted kind of novels. It's interesting to read. Let's see back a little bit. But very interesting style. So, that's named after Kafka. Then there's Delta Lake. This is an open source storage framework built on top of data lakes. So the name implies it's for data lakes, and it's somewhat a management tool for data lakes. It's open source as well. Then there's Kubernetes, which is basically a platform for container management. So you can actually run Docker containers below Kubernetes, but also different ones. There's Apache Airflow. As you can see, there's just a lot of stuff is coming out from the Apache Foundation. Now, if you wonder how this happens, you can see here that, for example, Airflow was originally developed by Airbnb. Airbnb it's also available here, but in the US, it's I guess also in many other countries like Germany. It's a big platform for renting apartments. And this was originally developed by them and then put into open source. So a lot of these Apache projects are actually originally developed by some large company, and then later they decided to put it into open source so others can work on it and improve the code as well. And of course, the idea is that somehow the community will spare the money so other people will do unpaid work on the project. But of course it has some benefits as well for the community. Then there's Apache Parquet. Parquet is a column-oriented file format for big data applications. I won't go into bigger detail here, but Parquet is also the format which will you might also stumble upon. So it's the basic idea of column-oriented file storage is that often in big data applications you don't want to read an entire row of data, but only certain columns, and then it's more efficient to store column-wise than row-wise. Conventional, like usual relational databases, usually store the data in row by row. So of course, if you're only accessing certain columns, then it's more efficient to do this column-wise. But if you always need all columns, then of course it's not. So Parquet is also something you can natively access with operations offered by the framework at least concerning Spark. Then there's Apache Cassandra, which is also a column-based distributed NoSQL database. Apache Org, which is a column-based data format, it's quite similar to Parquet. And RC-File, and RC-File is another column-based data format, similar to Org and to Parquet, originally developed by Facebook. So, as I said, lots of this stuff are basically just tools which have been developed by one of these big companies, and they decided to put it into open source. And this, of course, this list is far from being complete. So there are many, many more frameworks. Some are rising, some are falling, and it's difficult to actually get a snapshot of what's currently going on, because this whole landscape is really moving. Okay, now let's look at fundamentals of Spark. Spark has several components which you might view as the Spark ecosystem in a narrower sense. So in a wider sense, it's all the stuff I just introduced to you. But in a narrower sense, you can say that Spark consists of the Spark core, and then also some modules which are directly part of Spark and developed by the same people behind Spark. That's the Spark SQL module. And there is a module called MLlib, another module GraphX, and a module called Structured Streaming. And the Spark core is a module which itself can be divided into 4 submodules, which are basically just for bindings for the solid languages. So there are bindings available for Java, but as well for Scala, for R, and for Python. But the bindings for R and Python are not feature complete, I guess. So there may be some differences. So if you want to access the full power of Spark, you might stick to Java or Scala, which is pretty much the same, and it's running on the same virtual machine. SQL, of course, is about SQL statements, and MLlib is about machine learning. GraphX is about the representation of graphs, and structured streaming is about streaming-oriented processing. I will come to that later. Okay, so now let's first look at the Spark core. What is the Spark core? The Spark core is basically the core functionality of Spark. All the I/O operations are defined and implemented in the Spark core. It's also about cluster formation and control. This is all part of Spark core, of course. The task distribution from the nodes. Also everything regarding fault tolerance. The calculations are performed entirely in main memory. This is a very important feature of Spark, which is of course also part of the core. As I said, if you compare this with the MapReduce framework, in the MapReduce framework we have persistence of intermediate results and storage, which is gives us very bad access times, of course, because even SSDs are always orders of magnitude slower than RAM. So Spark always tries to do everything in the main memory, and if this doesn't work out, then it's able to persist actually with the configured data, but it's not trying this by default, only if there's no other option. And then there is one built-in distributed data type, which is called the Resilient Distributed Data Set, or RDD. So RDDs are the basic abstraction of sets of data in Spark, and everything else which you can find which works on top of RDDs is actually using RDDs under the hood. So whatever you do in Spark, you always somehow manipulate RDDs, even if it doesn't seem to be obvious. So it may happen that there's another abstraction, but under the hood it's still RDDs. So RDDs are the basic abstraction for data in the Spark core. The initialization of Spark is actually pretty straightforward. So like this, you can create a new config, applying the build-up pattern. You probably know the build-up pattern. So you can set an application name, set an application master. There are several ways to define application master. I will also explain this in detail later. If you want to run Spark locally without any cluster and exactly two parallel threads, you can just insert local and square brackets here and two square brackets here, so like this. And then it will run locally with exactly two threads, which can be quite handy if you want to test something, because if you're testing it with one thread, then you won't get any kind of errors which are related to parallelism, which may be a problem. So I would recommend for local testing to use this. And then you can create a Java Spark context, which is basically somewhat encapsulating the Spark context with additional stuff belonging to Java by just directing the config to the constructor of the Java Spark context class. Now we have Spark context, and our Spark context is basically the anchor of all Spark comments. So you can communicate with the framework via the context, and this context is of course available throughout your main program, which is called the driver. As I said, there are different representations of data. The oldest of these is the Resilient Distributed Data Set. Basically, an RDD is a type set of data to be processed in parallel. So it has some generic type, so it's introduced Java generics in type. And you can create it either from a local file, which must be available to the driver program at least, or from a source supported by Hadoop's input format interface. And HDFS, of course, implements this interface, but you could implement your own input format instance, right? So if you had your own custom-made distributed file system, whatever you would like to have as an input, you can just implement the input format interface and wire this up with your own stuff. But most often this is HDFS is used, or NoSQL or something else like this. Be careful with local files, because they should be available to all nodes, not only the driver, otherwise you have a problem. Then data sets. Data sets are a more recent concept which has been introduced with Spark SQL in Spark 1.6. So basically the data sets can be generated from the GBM objects. They can be processed with functional transformations, and the API is available in Scala and Java. This is an abstraction which actually under the hood uses Spark SQL, which under the hood uses Spark Core, which uses RDDs. So all data sets basically are transformed to RDDs and become to this data. But they can be more convenient than RDDs. And then there are also data frames. Data frames are basically just data sets with named columns. So it's just basically a different view on the data sets. And conceptually, they correspond to a table in a relational database or a data frame in R or Python. So the representation in Java is basically just a data set of rows like this. So you can use data frames pretty much like you could use an abstraction which works on top of a relational database table with the named columns. While the data sets actually have, Java is aware of the type, so they are actually strongly typed. Now let's first look at the RDBs. RDBs can be generated, for example, with the parallelize command method. You can also denominate the number of partitions. This is the initial number of partitions because it might, of course, change later. So if you don't, you can omit this parameter. So you can say, pick the number of partitions as you like. Then, of course, the framework will decide how many partitions should be correct. And as you can see, it's pretty straightforward like this. So, for example, here we have a list of integer values, and now we can just call from the context, parallelize, call data, and now we have an abstraction of an RDB. And now we can do the same also from external data like this. So there's a command called text file, which would give you like an RDB of the type string. So there are several ways to create this RDB out of actual data. However, as I said before, so be careful that local data must be locally available on all nodes. So you may refer to the data on a network file system like network attached storage. So that's fine because all nodes are connected to the network, so they can access the network share location. But be careful to actually point to a local file, because the local file must formally be replicated to all nodes in order for this to work. Because if you don't, then if you test it, then it will work on your local machine, of course, because the data is here. But once you are using it on the cluster, it won't work on any of the nodes. So one of these kind of errors which only surface once you run on the actual cluster. So it's a better idea to actually refer to a network file system or HDFS or something like Amazon S3. You can also reference directories or wildcards and zip files. This is all possible. So there are some convenient commands to actually unpack zip files, for example. So several ways to get the data into Spark. Some further options to import data. There's this method, old text files. This reads a folder with links for text files. It returns pairs of the form data name and content. That means the entire content becomes one single data set. Compared to a text file, where in text file you have, it's divided into different rows, so one for each line. And basically any data which is in the Hadoop input format, as I said, which implements this input format interface, can be read with the Hadoop RDB command. You can also save RDBs quite easily using the Java serialization with save as object file. But in most of the cases, it's not a smart idea to save RDBs this way when it comes to this data. But you can do it for at least. Then, the most important concept of Spark are so-called transformations and actions. Transformations are basically protections which are performed, for example, with the map command. And actions are performed, for example, with the reduce command. Transformations define a mapping function which always defines the transformation of a set of data into another set of data, but not necessarily bijective transformation. So if you call the map functions in the Spark driver is always the main problem, so you always define to start with a Spark driver program. And if you call a math function from the Spark driver, well, nothing happens at all, except that the framework internally builds an execution graph. So it looks like it's doing nothing if you run a transformation, but it is doing something. So it's a so-called lazy evaluation. I guess most of you are probably aware of this concept. So lazy evaluation means you are basically you're being lazy, so you only work what you really have to do. And if you're able to postpone something, you will do this as long as the data are not actually required to process. And that's what Spark really is keen on doing. So as long as you only define transformations on your data, Spark will just build an execution graph and add this transformation to the graph, and then continue in your driver program. Actions actually define a method which really makes the cluster work. So actions enforce calculation because of the nature of the actions. So they actually run the entire cluster. So an action is actually something which creates some kind of application on the cluster. So if you trigger an action, then your execution graph, which has been built until now, will actually be forwarded to execution to the framework. And actions are methods which can only be evaluated by performing the actual calculations. And one example is reduce. In order to evaluate reduce, you must actually trigger a calculation, but also like count, because if you want to count how many elements there are in the data set, you must actually calculate everything, because otherwise you would know, right? For example, if you would filter the data, then you would need to evaluate the filter expression, so you don't know how many elements are still left. So count, any count will also trigger, count is an action, so count will also trigger the execution of the entire cluster. Even if you just want to know the number of elements of an IDE, which is often the case if you are debugging into something and if you're playing around with it a little on your local machine. But of course it's interesting to know, for example, if a more or less complex filter condition, does this really apply to 1% of the data or 50% or even more or less, so it's an important difference, right? So in order to actually find this out, you need to have a count, and the count will actually mean that the program is executed. So consider this when you're debugging something, because you might use a count just for debugging purposes, and if you then later do not remove the statement, then you will have the entire cluster running just to calculate the count. It's not a good idea, right? So, once you have understood what you want to understand, comment it out or delete it the data. So be aware that every count is an action. Every action will actually trigger the execution of the cluster. So the cluster is run as soon as the execution of the Spark driver program encounters the first action. Before that, it will only build up the execution graph and do nothing else. This also means that you cannot debug into any RDDs. So if you debug into the RDDs are just an abstraction. So you see like some pointers and whatever, but you won't see the actual data. Because the data are only read into the RDDs once the cluster is being executed, not before that. So it can be disappointing, to try to inspect an RDD on the debugger, because at the time the debugger is on the transformation level, you won't see anything. Just management structures. So what are important transformations? Of course, there are several others. These are, I would say, the most important ones. First of all, the map function. So what is the map transformation doing? It creates a new RDD where the defined function is applied to each element of the old RDD. So it's element-wise. And of course, you have to be aware that it's element-wise. So if you have a large number of elements, then this function is called every single item, which can be quite a lot. So what you should not do is have any kind of illustration stuff which is, for example, once per node or once per partition. So that's a bad idea to have this defined in the map function, because every time for every item, all your overhead is being created again. For example, if you have a database connection, it's a bad idea to define this in the map transformation. Then, yeah, filter, as the name says, it creates a new RGB, which only contains elements where this function evaluates true, basically filtering out everything else. Then there's this map partitions, and that's quite useful because it's similar to that, but it's executed separately on each partition of the RGB. So it's called as often as you have as the number of partitions you have. So if you have 5 partitions, then map partitions will be called 5 times overall. And if every partition consists of 10 elements, then for example map would be called 50 times, but map partition would be called 5 times, so once for each partition. And then the function of map partitions is of this type iterator of a certain type is projected to an iterator of another type if the RGB is of the type. So of course the resulting, so the iterator, the implementation of your map partitions function must create a new iterator of a new data type, which can of course be the same as here, but doesn't have to be. And it gets an iterator. So always you implement a map partition so that you iterate over the iterator you get, create a new iterator, and transform the data somehow. And then it's done once per partition. Then there is the function sample. There's a Boolean flag for its sampling with or without replacement. And then there is a fraction and a seed. So the semantics is that it is for an example of the specified fraction of the RGB with or without replacement, and using the specified seed for the random number generator. Be careful that you're using a different seed. Or you could use, there are many options what you use for a seed. For example, programs are sometimes using latency between 2 mouse movements as a seed or something, so it must be somehow something that should be as random as possible. The best randomness you can get actually is Pisay, so atomic Pisay. The most random signal you can get in nature. Yeah, it doesn't have to be that one, but basically if you're using the same seed, you might end up deterministic, so you might end up with the same same values. So be careful, even though it's called a random number generator, it may work somehow deterministic if it's using the same seed. Actually, there was a very well-known problem, or nowadays well-known, with I guess OpenSSH. Maybe you've heard about it. It was some years ago, and the problem was that they OpenSSH, you may probably know, is not only simple, but it's basically the encryption tool used for encrypted connections. And the error they made was that there was a line in the code to pick randomness, and so it's what it did is it read from the place in memory without prior allocation. So usually, if you don't do this, right? Because it's not a good idea to read from something that you haven't allocated before. So this created a compiler warning, and then some guy in the OpenSSH team got this compiler warning and said, "Wow, let's get rid of the compiler warning." So he just commented out the seed for this memory read. And now it's still C to back. So I said, "Well, great, the compiler warning is gone." And now, I have improved the program because I removed the compiler warning. But what he did, of course, was that, he now narrowed the key space down to, I guess, like 2 to the power of 16 different values, which are like 65,000 or something. So, which is, of course, any computer can just iterate within a couple of fraction of a second. So, not a good idea, right? So there were only like 65,000 different private keys being generated by OpenSSH after this change. But no one noticed. So that's a really funny thing. So no one noticed. And this really went through, I guess, 2 or 3 years until someone actually noticed that there were only like 65,000 different keys being generated. So all this time, this was like absolutely inherently insecure and no one noticed. Or maybe some secret services noticed and said, "Hey, great, let's keep it this way," I don't know. But so you can see, maybe even a guy from a secret service did this, I don't know. You can see that be careful with random number generator seeds. They usually serve their purpose. Also, you can see that it's a bad idea to only mechanically look at like compiler warnings and I want to get rid of compiler warnings, but understand what the code is all about. Yeah? So now thinking using the brainstorm is a good idea. And so we can pick a seed here. Then union, basically does what it says. So you create a union of two IDs. You can also create the intersection. You can also get distinct. So and remove the duplicates of a set. Then you can group by a key. Of course, if the set has the form of KD, then it groups by K. And the result will be all these which belong to the same K. Then there is this reduce by key, which is doing a reduction by using the applied function, the provided function. So it aggregates the V's with the same K using the given function. This function, of course, projects two elements of type V onto another element of type V. So we are basically joining two items to a single one. The way you define it, of course, in the function. And then we have this repartition, which is also quite important because it redistributes the data in this RDB randomly across the given number of partitions and tries to balance them. So it's a good idea to call a repartition once you have somehow changed the distribution of the data. And this is usually the case if you are working on something which isn't like is not injective, right? So if you have bijections, then of course the number of partitions, if you pick them initially in a good way, then it will stay this way. But of course you may like create sets of sets or whatever, and it may just shift. And so later you may be imbalanced, and if you want a cluster to behave efficiently, then you should of course do a repartition after that, so the data are redistributed in an even manner. But of course be aware that repartition will trigger a shuffling, so of course the data will be sent between the nodes because they are there beforehand. So these are all transformations, which means that the result of each of this operation is another RDD, and the transformation, as I said, will only contribute to the execution graph. Some examples. I guess this is pretty straightforward. So you can see, for example, 1, 2, 3, the methods on x plus 1 will be 2, 3, 4. If you would use a filter statement on the same set, like let's pick out the x's larger than 1, we will get 2 and 3. If you would create a union of 1 to 3 and 4, 5, or 1 to 6, 4, 5. Intersection of 1 to 3 and 2, 5 would be 2 only. And if you want to have duplicates in your set, which can happen because as I said, these are sets, right? So if you want to have them create a distinct set, use distinct, and then it will create a distinct set. But of course be aware of the comparator which is being used for this, because you must have a definition of equality for this to work. For a non-trivial kind of data, think about that's really what you want. So if you're not giving in a comparator, then it's using a default comparator, and this may not be what you want. Then this group by key statement. That's also pretty straightforward. So if, for example, the 1 would be mapped to A and also to B, and the 2 would be mapped to X, then we do group by P, then our 1 will then be mapped to a set of A and B, and the 2 is still to X. And if you would reduce by P, and the reduction would be the concatenation of two values. So in this case, we create a string of both, so because 1 is mapped to A and to B, the concat operation will lead to AB, and the 2 would be projected to X. So, I guess pretty straightforward. What are important actions? as I said, actions will actually trigger the execution of your execution graph. But why? Well, for example, the reduce action aggregates the elements of an RDB using a given function. So the function is of type A is projected to another instance of A. And of course, it's not commutative and associative. Well, ask why it doesn't need to be commutative. So, associative, we talked a lot about this, right? It's the same as with Hadoop. But it also needs to be commutative. So that the order of the operands can be permuted for optimization. So Spark is actually optimizing the execution. And as long as it's still building up the execution graph, and you're adding some more transformations, it will actually rethink the entire graph, and it might, permute the order of operands. So it's more efficient. And for this, of course, to work, the function needs to be commutative as well. And then we have a collect action, which is it returns all elements of the RDD as an array to the driver. Now I say here, this should be in red, I guess, it says caution. So why do I say caution? Why do I say caution with collect? Should be twice as big, I guess. So it's not prominent enough, maybe. Why is it dangerous to call collect?
Like if you have a small data set, it would be fine-ish. But once you have like big data rolling in, then take every single data that's distributed right now back to the main program.
Exactly. So the talk is think of a really big cluster, and what collect does is like it's like contracting your entire abstraction down to a Java list. So it's really just collecting everything from the entire cluster, all your data, back to the Spark driver program, which is just on a single node. So all the data that you collected. Now, if you have, if you didn't do this for a very small subset of data, or to somehow very large aggregation state, data aggregation stage, so very small kind of data. So, but if you do this with your raw source data, this is almost never what you want, because it will just, it will just break the cluster, it won't work. Or it will take bloody ages to finish, because you're just collecting like terabytes of data. So this is something which might actually happen quite often when debugging something, and you, for example, then you had moved a comma with a sampling or something, or you didn't do a sampling at all. This is also a good idea if you didn't do big data stuff. So be really careful with the collect statement, and it's I guess there's a ranking of Spark anti-patterns, and number one is, I guess, the misuse of collect. So be very, very careful with the collect statement, and be sure that you're not collecting like all the raw input data of the cluster. Usually you only want to collect results, and quite often you do not really collect them to the, collecting means sending them all to the single driver node. This is usually not what you want. I mean, usually you will process them and aggregate them in some more or less sophisticated manner, and finally you write the results, for example, to an S3 destination or whatever, some kind of aggregated statistics. Usually all this big data stuff will be condensed to a very small data, output data. And in this case, you don't need to collect the data. So be careful with the collect statement. The same goes for count. Count is basically the same. So because actually what Spark does is if you call it count, it also does it collect, because otherwise it won't be able to know how many elements are in the set without actually calculating the set, right? So you need to do a collect first to do a count, which is what Spark does. So as I said, be careful with the count statement as well. Of course, it may be needed for debugging purposes, but then, as I said, first draw a sample, count a sample, and then you can get an impression of how much data you're talking about. Be aware that as collect as well as count will cause the entire cluster to send all the data which are extracted away in the RDB to be sent to the driver node. Then first returns the first element of the RDB. You can also say, hey, I want the first n elements of the RDB, so we take n. You can say take a sample, which returns then a sample with or without replacement of the IDE. You can also take an ordered sample, and you can, for the order, you can define your own comparator. As I said, it may be a good idea to have your own comparator, depending on what your idea of equality is. Then you can call it save as text file, which saves the RDD as a text file, either locally or in HDFS. You can also save the RDD as a Java serialization file, which can then be recovered with object file, which in most of the times isn't a good idea, but still it's there. And then you have for each, and for each applies the given function to each element of the IDE. But be careful, because if you want to count across the class, that doesn't work the way you might think it works. And if you actually want to count correctly, you need so-called accumulators. I will explain what accumulators are. So it won't work without accumulators. That's because of the way Spark works. First about persistence. So I said a very important difference to compared with Hadoop is that Spark by default can hold data in memory during operations. And this is called persisting or caching. So persisting is the idea, it's a bit more frozen. So the idea of persisting is it's somewhat less kind of storage involved, and caching is more the idea of keeping it in run. But it's basically the same concept. And persisting in RDD means that all completed partitions within a node are kept in memory and are reused for further operations on the RDD. So the idea is that you want to not have to recalculate anything, and you can mark RDDs as persisted using the persist or the cache method. If you don't do this, then after an action, everything is gone. So if you had built up a long execution graph and then trigger an action, and then it's all the data are being processed through your execution graph, and then all the intermediate results are thrown away. So so be aware of that. So if you want the results to be somehow reused, you need to use the cache method of the RDD or the persist method. And cache is basically just short for persist with persist with the memory only option. And for persist, you can actually set one of these storage levels. So you can assign a certain storage level to each persisted RDD. If you're using cache, it will use just memory only. But if you use persist, you can pick here. So what are the storage levels? Memory only, which is the default, as I said, for cache, means that it will only be persisted in memory. And if you run out of memory, then individual partitions will not be cached, and they will be recalculated as needed. So as always, if Spark runs out of memory, it has to do something. So it does not cache your individual partitions. This is why you also have the option to pick the level memory and disk. So this works like memory only, but the partitions that don't fit into memory are now not recalculated but stored on disk. So this can be faster, of course, than recalculating, and they can also be slower. So be careful, because it really depends on what's fast, right? Your CPU time or your storage. And often the CPU wins, because if you're doing really trivial calculations, it might be cheaper to do the recalculation than to wait until your storage has given you back the data, because loading is I/O, and I/O is also expensive or can be very expensive. So, of course, it may be that you are doing some really difficult, heavy calculations which take a long time. So in this case, persisting may be a good idea, but very often the CPU wins against the storage. So, in other words, so CPU power wins against I/O. So be careful that this is a trade-off. And there's a reason why memory only is the default and not memory in this. Yeah, because most of the times it is a better choice. And if not, then you need to be aware of this and why. Then there is memory only SER. Yeah. This is the same as memory only, but the persistence in memory is done in a serialized form. And this is, again, it's some kind of trade-off. So it saves the storage space because data takes less space. If it's serialized, then it takes if it's unserialized. But it requires more CPU power because in order to access the fields of the data, you always need to deserialize it. So the deserialization is added effort for the CPU. So this is more balancing towards requiring more CPU power, but to gain space. So you're saving on storage, but on the price of CPU power. And then there is disk only, so you're only persisting on disk. Level memory. This might be useful if for some reason you really have not so much memory and you need to be very careful with what you're doing with memory. And by the way, this is like the default behavior of, this is the only possible behavior of Hadoop. It's only persisting on disk. That's what makes Hadoop so inefficient. And then, you also have the option to replicate every partition on 2 nodes. I guess there's also the option to replicate a partition on 3 nodes. So, this is just if you think that calculation is so expensive that you really want to be sure that the data not gets lost, so you can replicate it on more than 1 node. Very rarely this makes any sense. Okay, so as I said, counting in Spark is a little more difficult because you always have to be aware that what is happening on your driver program is not happening on the nodes, on the slave nodes. Only any kind of data which shall be present on the slave nodes must first be serialized and sent over the network and then deserialized on the destination node. And this doesn't come for free. And especially it doesn't apply to class variables. So if you define class variables on your driver, you can of course do that. As you can, it's basically just a Java program running in the JVM, yeah. So you can do anything you can do with any Java program, like defining class variables and also assigning large loads of data to them and so on. So everything's great, unless you want to do something with them from within a Spark action or transformation, because then the data will not be available to the nodes. Except for one node, which is the same as the very machine where your driver program is running on. So you may not stumble up in this testing it on your local machine, but once you have a cluster of class, this will be a problem. Class variables can be defined in driver, but are not available on the other nodes because only data that are passed as parameters to the operations and serialized for exchange over the network are transferred to the other nodes. Note that this also implies that the data must be serializable. So data which is not serializable can also be not transferred over the network. But there's a mechanism to compensate for this. And this mechanism is called broadcast variables. So what do broadcast variables do? They allow for caching a read-only variable on each node. And it works like this. So let's say we want to broadcast this integer array of just 3 numbers. Then there's this wrapper class called broadcast. And this is the type of your broadcast. Now we have a broadcast which is typed with this integer array. And then we create it like this. So the Spark context has this method broadcast. And we say we want to create a broadcast out of this array. And now we could, for example, just print out the contents of this array by using the value method from the broadcast. And now we have this broadcast, and this is actually available to all nodes because the framework is actually available. Of course, it's not is magically happening when it's doing this. And we can also remove all resources of the variables temporarily or permanently. This driver remove the resources permanently. So if you have if you have a broadcast which is not required after doing some initialization stuff or whatever, it's a good idea to actually destroy it so the resources are free and can be used in the node for something different. What are typical applications for broadcast variables? Actually a lot. So for example, lookup tables. This might be handy for extraction from load pipelines. So we want to have, if they are small, so it's not a good idea to have like really big amounts of data on the broadcast variable because it's blocking the resources in every node. But for small lookup tables, it's quite handy. Also for configurations, for filter lists, and in general for joining a small table on a big table. So in this case, the small table is what you are broadcasting. And for example, you have a large log file and you have a small config table you want to join on. Why? Because well, you have no shuffling going on because it's faster to join. So yeah, it's faster because you have no shuffling going on because the data is already there. So it may also be handy for the inference step of machine learning models, or in general for the caching of expensive objects per executive. So there are some applications. Here's an example how lookup tables might be implemented with broadcasts. So here we have actually two broadcastings. No, we have one broadcast. So here we have a hash map, and the hash map has basically the assignment of a user ID to a user, like this. So number 1 is John, number 2 is Alice, number 3 is Hans. And now we create our users broadcast with this hash table, and then we can, for example, on the nodes, we have some kind of data which only has these IDs, and then we want to look up the names for the corresponding IDs without having to do any kind of joining data or acquiring data from anywhere. So what we're now doing is, like here, we're just using resolving it using like this. So it's projecting to the value of the broadcast user's value. If you use this get or default, then if it's not in the lookup table, it will just return the string, except the string. Right? So for number 4, it will return on the table. And now, for example, we could use a statement like this to actually output, John, Alice, Hans, not in table, right? Because now on our node we have this array, and then this would actually create a string which resolves the mapping of the ID to the string by using the broadcast variable. So no deployment of tables necessary. So as I said, it can be quite handy to have this broadcast. And now let's get back to this problem with counting. So I said that counting in Spark is different. So Spark does not always behave identically in a cluster if you compare to local execution. And most of the times it's more difficult to make it work in a cluster, as always. So because there are things which can happen in a cluster which don't happen if you run it locally. What are this is an example for this. So now we define a variable counter, and then we parallelize some data, so we create an ID out of some data. And now, we want to actually increase the counter as we iterate over the data of the ID. And you see here, it's it says don't try this at home. So why does it say don't try this at home? Because the value we get here will not what you would expect. Unless you are only running it on your local system. In this case, it will work, but it will work because everything is with this one Java virtual machine. But what Spark doing here is it decomposes the ID operations into tasks, and these tasks are executed in parallel by the executors. And in order to work, this data must be serialized and then sent to all executors. And now the problem is that the counter of this driver node, so this is local variable, so it's defined here locally, so it's not visible to other executors, and all other executors except the one we are on the driver node is 0. So the counter is still 0 on every node, and you will end up with a value much less than you would expect. And but if you run it in local mode, the code can actually be executed in the same GVM. In this case, the counter will be correct. So it's one example of an error which will only surface when running in a cluster. So be careful that not everything you see in your local JVM environment is what every cluster node can see. The clusters can only see what has been serialized and sent over the network. So either use broadcasts to make the data available there, or send them as arguments for transformations or actions. And basically there are not many other options to do that. But there's a nice abstraction to make Spark, for cables like this, to make Spark count as it should. And this is called accumulators. And accumulators can be used for correct counting because they are somewhat restricted. They can only be added to an associative or cumulative operation. Like this. So we may create an accumulator. It's again some kind of object which we get from the context. And then we don't just add it within our bound focus also for each statement, but we are using the add method of the accumulator. The accumulator ensures that it's actually done in an ordered manner. So if you finally then retrieve the value of the accumulator, this is really 10, so all this sum of this, also if you execute in the cluster. So the accumulator can count correctly. But if you don't use the accumulator but do it on your own, you will fail. So memorize that if you want to count on Spark correctly on the entire cluster, use accumulators. And of course there may be some valid reasons why you may want to count, even though it's not so common, I would say. But like in this example, we might have a text file, and you're reading this text file into an RDB, and now we want to count the number of valid records and the number of invalid records. And let's just say that a valid record is a record where the split method will lead to 3 different fields. So less than 3 or more than 4 fields in the text line, so that the split method will give us another value. We say it's invalid, so we add 1 to invalid, and otherwise if it's valid, we add 1 to the valid accumulators. We have to accumulate for valid lines and not for invalid lines. And now if this has been processed, we can just query the value property of the value method as the accumulator, and it will give us the accurate number of the lines. So just an example how accumulators could be used. But of course, I would say also for this case, there are more elegant way to do this. But still, you can see if you want to count, you can use accumulators and it will work. Okay, so far for this. Then, let's have a 15-minute break and then we will continue with the exercise.